Alright, so between now and the end, so today we're going to cover this. Monday we'll have a little bit more, Tuesday a little bit more, Wednesday. I'm going to introduce this, it's called an hour of code, and then it's on you to do it outside of class. If you choose not to do it, kind of sucks for you then. And then Thursday, Friday, so Wednesday, Thursday, Friday, we will, during class time, so this will be, the intro will be probably about 15 minutes, but then the rest of the class, and the rest of the class for the rest of these periods is doing review for the final. And then the Monday, a week from this coming Monday, we will have part one of our final. And then we decided Tuesday was when our final was? Okay. Calculator's totally chill to use. I do have a couple in the drawer that you're allowed to use, but try and figure out getting a calculator just in case there's not enough, because I know that sometimes you're like, oh, it's always going to be there. Well, it might not, so just be cautious about that, okay? But this last section we're going to cover, we're just going to cover one portion of it, and it has to do with graphing lines. So if you graph two lines on the same xy axis, or if you graph two lines on the same Cartesian plane, or if you graph two lines on the same coordinate plane, or however you want to mention it, those lines can do three different things. They can be parallel to each other, which means they would never, ever, ever cross, and that means there's not a solution. They can intersect each other, which means the point that they intersect is the solution. So the point where they intersect happens to lie on both lines. And then the last thing, and this is kind of, I always thought this was kind of weird, is if it's the exact same line, it lies on top of one another, there's infinite solutions. But it almost seems like, well, duh, if I have the exact same line, why would it not be an infinite solution? But I just needed to talk about that real quick. So let's go down through these. So the first equation is y equals 2x minus 3. We know that my y-intercept is going to be, what's my y-intercept in this first one? Negative 3. So I'm going to go 1, 2, negative 3. And then my slope from that point, I'm going to go up 1, right 2. Or excuse me, up 2, right 1. And this one just keeps going like this. And I'm going to do this because it's 2 over 1. So you go up first. Okay? And then the same thing, I could go down 2 and left 1 because these are both negative. Negative over negative is positive. Do you agree? Yeah. So can you see that those points would all fall into a straight line, the bigger points? So a little wavy, but don't judge, please. Okay, so that's that first line. Second line, my y-intercept is going to be at negative 1. And then what's my slope? X, which is 1 over 1. So from this point, I'm going to go up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. So take a look at what this line's doing. Down 1, right 1, left 1. Does it appear those two lines have intersected each other?
Yeah.
Can you see that okay? That makes sense?
Yeah.
So the point of intersection is the solution to the problem. So this point right here is 1, 2, up 1. So it's the point 2, comma 1. Okay? That's the solution to the problem. Now, intersecting points are indeed something that business and industries do use. An intersection of two different types of graph, whether they're straight lines or curved lines, does mean it's a solution to the industry. If I were to take 2, comma 1, which is x and y, and if I were to plug them both into both of them, I'm going to get 1 equals 2 times 2 minus 3. And if I plug into the other one, I'm going to get 1 equals 2 minus 1. So 1, what's 2 times 2? 4? So 4 minus 3 is how much? Is that a true solution? If it's a true solution, it means it exists on the line itself. Okay? And on the second one, if I did the same thing, I'm going to get 1 equals 1, and that's also true. So the point 2 comma 1 lies on both the red and the green lines. Okay? It happens to be the intersection of the two lines. That's the solution to the problem. So graphing, though it has a valuable spot, graphing by hand sometimes is a lot tougher because you're not completely accurate on your graphs. So if you think that it's going to cross at a particular region, what you can do is you take that particular point you have found and plug it into both of the equations, and you're going to find that you have a solution to the problem if it's correct. If this is not a true statement or this is not a true statement, that means that's not the solution to both of those problems. Okay, a system of linear equations, it is two more linear equations together. The solution of the system of linear equations is intersected at a point, the point that they have in common. So they're asking us, problem number 1, if 4 negative 3 is the solution to that first system, and then problem number 2, they're asking if that's the solution to the second system. So what we're going to do is I'm going to plug this x and y value in to both of these, and if I get true on both, that means that that point lies on both lines. If that point lies on both lines, that means it's a solution. Okay, so if I take that first equation, I get negative 3 equals negative 2 times 4 plus 5. So that's negative 3 equals negative 8 plus 5. Does that mean negative 3 equals negative 3? So is that enough to say that that point is the solution to both of those lines? No. That means this point exists on this line. So now I have to see if this point exists on this one as well. So I'm going to take this, do the same thing. I'm going to take 4 and negative 3, plug it in. So I'm going to get 4 plus 2 times negative 3. Is that equal to negative 2? Is 4 minus 6 equal to negative 2? Well, yeah, that means that negative 2 equals negative 2. So that point happens to lie on both of those lines. It's true in both of the situations. So being that works, this is a solution. Okay? If I were to graph those 2 points at 4 to the right and 3 down, the 2 lines would have intersected each other. Does that make sense? All right, let's come around the room and see how we do. All right, Ben. That's a point, correct?
Yes.
Which is my x value, which is my y value?
1 is x.
1 is x, and?
5.
Okay. George, do you agree with that?
Yeah.
Seems okay so far? Okay. Bo, what do you feel I should do with x comma y, which is 1 comma 5, with the very first problem to verify if that point exists on there? Okay? So I'm going to plug in for both x and y. Do you agree with that? So 3 minus equals negative 2. That was an x. What's going to go there now? A 1. That was a y. See how the negative came down. So what plugs in for that? 5. Okay, 3 times 1 is 3, right? Steve, what should I do with this? What happens right there? Technically, yeah, it's basically like saying negative 1 times 5, which would be negative 5. And let's see, Crystal, if I go 3 minus 5, what number do I get? Negative 2, good. So I get negative 2 is equal to negative 2. So Gage, being I came out that negative 2 is equal to negative 2, I think that's a true statement. So what can you justify about 3x minus y equals negative 2 and the point 1 comma 5? does it lie on the line or does it not lie on the line? And what would justify if it does or doesn't? Good. So because I got a true solution, that means that point lies on that graph if I had a graph, that first one. Okay? Tristan, I'm going to take the same point and I'm going to plug into this right here. Is that okay? And if it gives me true on that as well, that means it's going to be a solution to the problem. So I have blank equals 2 times something minus 3. That's y equals 2x minus 3. So what value would I plug in right here where y was? 5. What value am I going to plug in right here where x was? 1. I'm going to do the arithmetic. So I know that 2 times 1 is 2 minus 3. So I'm going to get 5 is equal to negative 1. Ray, is 5 equal to negative 1? No. This is absolute nonsense, right? That's not true. So Preston, what do you think I could say about the point 1 comma 5 and y equals 2x minus 3? Does it lie on the line or not? What would you think? No. Why would justify it not lying on the line?
They don't match up.
Yeah, it's nonsense. It's not like we found some weird pattern in life going, dude, check it out. 5 is now equal to negative 1. Oh my gosh, things have changed, right? So this is not going to happen. So is the point 1 comma 5 the solution or the point of intersection for these two lines? What do you think, Reese?
I think it's
It works here. This gives me nonsense. Does it work for both? True on both?
yes. No, I'm just kidding. No.
True on one of them, not on the other.
Yep.
So it works on one and not on the other. It is not a solution. Even though it lies on one of the lines, give me true. Even though this happened up here, because this happened up here, that just means that these lines, they might intersect, but they don't happen to intersect at that particular line or that point. Did I say that clear?
Yeah.
Okay. So there's going to be times that you're going to have to plug in the value, the x and the y, to both of the equations and see it to work. Now, here's the nice thing. If I gave you two equations, you plugged it into the first one, and that becomes a false statement, you're done. You don't have to continue the problem. You can say, no, that's not a solution. It didn't work on the first one. It doesn't matter if it works on the second one. If I get a yes and a no, or a no and a yes, or a no and a no, that means it's not a solution to the system. The system happens to be two lines. If I got a yes and a yes, that means it is the point where those two lines would intersect if I had graphed them. Okay, so this first scenario, Mr. Kruger, can you see that okay? What do you think the slope of both of those lines would be?
What, together or like
What's the slope of the top one?
5? No.
That's the y-intercept.
2 over 1.
2 over 1 and the negative, right?
Yes.
So that is my slope right there. What's the slope of the second one?
Negative 2 over 1.
So that's the exact same slope. Same slope, right? If I have a line that has the same slope, is the y-intercept, do you feel the y-intercept is the same? Because I know Kruger said one of them's 5. Andrew, what's the other y-intercept of the other one? Negative 1. Are 5 and negative 1 the same number? Well, we kind of proved it on that last problem that 5 equals negative 1, but that's not a pattern. We know that. It's nonsense. So these lines happen to be parallel to each other. These are parallel lines. Parallel lines do not intersect. If they don't intersect, that means that there's not going to be a solution to the problem. Okay? So this has 0 solutions. Okay? Now, the second problem, I have a slope of negative 2 and I have a slope of 2. Negative 2 and 2 are not the same thing. Now, negative 2 and 2 are opposite signs. Are negative 2 and 2 reciprocals of each other, though? Is it a flip over fraction of each other?
No.
So, what is the reciprocal of 2? The flip over of 2?
1 over 2.
1 over 2. Okay? So these are not reciprocals. Though they're negative signs, This means that they are indeed going to intersect each other. They intersect right there. So these lines cross. Hey, do perpendicular lines cross? Yeah, they cross at 90 degrees. It's a special category. So they cross. This gives me one solution. What is that one solution? It's wherever this is. That looks like -2. That's -2, 3. How could I verify the graph is correct? I could plug it into both. And if we plug it in, I'm going to get 3 equals 4 minus 1. That's 3, works on top. And I'm just doing it real quick, I'm sorry. And on bottom, I'm going to get 3 equals 4, or -4 plus 7. -4 plus 7 is 3, so it works on the second one. So that is indeed the answer. So the solution to the problem is the point of intersection for the problem. So we can have 0 solutions, and we can have 1 solution. Now, I see only one line graphed up here. So if I graph this first one, I didn't even have the graph right. I don't have the graph right. Big jerks. So if the graph, this should be up +5 down 2, right 1. That's the first one. And if I did the cover method, I'm going to get, let's see, that's 2.5, that's right there. And I get 5, which is right there. What can you tell me about that point and that point? I don't know why this graph is here. What can you tell me about those 2 red points in relationship to the blue graph? They're the same. So this is the exact same line. It's just a line on top of itself. It's just the equation is written in slope-intercept form and standard form. Standard form means where you use the cover method to find where it crosses the x and y axis. Slope-intercept means I find the y-intercept and use the slope to find the second point. If I do that appropriately, I will find I have the exact same. So these are the same line. And again, I apologize if the graph is incorrect on the paper, but I think we've made it right now. So I have the same line. The same line, same equations, means that it's going to touch infinite amount of times. So every x and y value of one line matches up to the x and y value of the other. So if I have the exact same line, I'm going to have infinite solutions. Okay? So I can have one solution if they cross. If they're parallel, I have no solutions. And if it's the same line, I have infinite. What do you got, George? Yeah, and I'm videoing it too, but please, if you want to take a picture of it, go ahead. You can come up and get a better picture. And I'm actually willing to. Go ahead, give him a. Yeah, come on up. This is a photo op.
Yeah.
And it's also videoed if you want to see the video. God bless you. He just wanted to help you out. All right, can I move on? We good? Bo, you ready to go? You good? All right. So how do we solve graphing? So how do we solve graphing? Well, I'm going to graph both of the equations that are given. If they happen to intersect each other, I'm going to try and figure out what the xy value would be. If they don't intersect each other, I have to take a look to see if they are parallel, because this means they'd have the same slope. Let me ask you all this. Is it possible that I could have a line like drawn here on this, and then I could have another line drawn here, and they happen to intersect way, way out here?
Yes.
Yes.
So if they intersect way, way out here and not on our graph, does that mean there's a solution or not?
Yes,
It does. It's just I didn't draw my graph big enough, right?
Yeah.
And is it possible that they could intersect way, way, way over here?
Yeah.
Yes.
Or way down here or way over there?
Yes.
So if they intersect, so if the slopes are different, it's very possible that I just have graphs that I can't see on a 10 by 10 grid. Okay? So the very first one, y equals 3x plus 1. My y-intercept is what?
1.
1. And then my slope is 3 over 1. So I'm going to go up 3 over 1. And I'll just do this a couple times. 1, 2, 3 over 1. 1, 2, 3 over 1. I could go down 3 and left 1. And down 3 from that and left 1. Because down and left are both negative. Down 3. Okay? So that's what the first line looks like. The second line is not set up the same way, but the second one is set up to do what kind of method? Cover method. So 2x equals 6. So what's x you have to? Yeah, it has to be 3. 1, 2, and 3. Okay? And then if I cover up y equals what? 6. 1, 2, 3, 4, 5, and 6. Okay? So I think if I have this graph correctly, that looks like the point 1, and then 1, 2, 3, and 4. That looks like the point 1, comma 4. As far as the looks go, it looks pretty good. How can I verify if 1, comma 4 is indeed the correct solution to the problem? Plug that x, y value into both equations. Okay, that's x and y. Okay, so the first one, that's an x value, y value. So I'm going to get 4 equals 3 times 1 plus 1. 4 equals 3 plus 1. That's 4 equals 4. Is that true or false? So that tells me the point 1, comma 4 is indeed on our red line. And if I take that point and plug it in here, I'm going to get 2 times 1 plus 4. Is that equal to 6? Well, 2 plus 4, is that equal to 6?
Yes.
Yeah. So that tells me that the point 1, comma 4 also falls on the black line. And they happen to be the exact same points where they intersect. So the solution to this problem is 1, comma 4. Is that good? Feeling all right about that?
Yes.
Yeah.
All right. I'm not going to watch that solution. But how do you know if it's a solution? If you plug it in, you get an equal statement. Does that make sense? You plug it in, and you plug it into both. So plug into both. Plug point x comma y into both equations. If true for both, then solution. We good? It's that plug it in video.
I want to watch it again.
Oh, it's done. All right.
Do it.
Maybe
Why
come
is
back.
it even there?
Plug it in, plug it in. That's fine. Sorry. Solve the system by graphing each. So we're trying this. How do we try it? Garvey, y equals x plus 5. What do I plot first? The x, where the y, where? Where?
On the graph.
Good, where on the graph?
What?
Where on the graph?
I don't know.
Y equals x plus 5. So remember, that's a 5. So that's 1, 2, 3, 4, 5. Garvey, what's the slope of? Is there any number in front of x?
There's an invisible one.
An invisible 1, and invisible 1 is the same thing as invisible 1 over 1, right? So that means from this point I'm going to go up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1. Is that all right? All right, Garvey, picking up on you again. Picking on you again. What is the y-intercept of y equals negative 4x? Where'd you get a 1 from? Help me
I
out.
don't see any.
You don't see any? If you don't see any, that must mean what?
What?
If you don't see any, what does it mean? No. If you don't see it, if it's invisible, if it doesn't exist, it's gone.
0.
0. What's my slope of this one, Garvey? 4. Negative 4. So I'm gonna, from this point, I'm going to go down 4, right 1. And that would mean I could go up 4 and left 1. So up and left is also negative, because up's positive, left is negative. Garvey, does it appear that the green and the blue lines intersect each other? That means they cross. And I know you'd have to squint pretty hard to see that, so it looks like negative 1, 1, 2, 3, 4. I'd say negative 1, comma 4 appears to be my solution. What do you feel I should do with that to make sure I am 100% right? Plug it in. Okay, so that's an x value and that's a y value. If I plug my x value and my y value, and I get 4 equals negative 1 plus 5, that's 4 equals 4. Checks here. If I plug it into the second one, I'm going to get 4 equals negative 4 times negative 1. Negative 4 times negative 1, I think, is 4. It works on both. What's my solution to this problem? Negative 1 and 4. Yo.
So for negative 4x, don't you go on the x-axis and go back 4 to the left 4? Because it went down.
This one?
Yeah, for negative 4x.
So down and right is negative. Down is negative, right is positive. So negative over positive is negative. That's why. All right, your assignment is going to be on page 121. It is worksheet number 1A as far as this unit goes. And I think if you were to do 1 through 9 odd, we'll double check that in class and then finish it in class on Monday. What do you think? Is that horrible?
Yep.
Aaron?
Yes.
Do I?
Horrible.
Do I?
Do you have food?
Do I have food with me right now?
No.
Oh, I doubt it. Sorry. I wish I did.
Some guys.